Welcome to our third set of mathematics practice questions for this course. In this video, we will dive into practice questions involving calculus. Ensure you have the FE Handbook open and reference its material throughout this lecture, as you must become familiar with it before exam time. As a supplement to this course, check out the full-length practice exams and other topic-specific practice questions that can be accessed through the link in the description. These practice exams are the best way to prepare yourself to take the actual FE exam. Follow the timing requirements to mimic testing conditions and review the detailed solutions to learn from your mistakes. Moving on, let's get started with some mathematics practice questions. Practice question 1. Solve for the area bounded between the curves f of x equal to x squared plus 1 and g of x equal to 3x over the interval where the curves intersect. What is the approximate area enclosed between the two curves? To solve for the area enclosed between two curves, the first step is to determine where the two functions intersect. That means we set the two expressions equal to each other and solve the resulting equation. In this case, we equate the quadratic expression to the linear one and move everything to one side to get a standard quadratic equation. Solving this using the quadratic formula gives us 2 points of intersection, which will become the bounds of our definite integral. Next, we need to determine which function lies above the other within the interval of interest. By plugging in a sample point between the bounds, we find that the linear function lies above the quadratic one. Therefore, we subtract the lower function from the upper one to set up the integrand. The resulting expression is simplified before integration. Once we have our definite integral set up from the lower intersection point to the upper one, we compute the antiderivative. This involves applying basic power rule integration to each term of the simplified difference between the functions. The result is a single polynomial expression as shown. The final step is to evaluate this integral at the upper and lower bounds to find the total area between the curves. After simplifying, we find that the exact enclosed area is 10/3. This answer matches option C. Practice question 2. Find the local maximum value of the function f of x equal to 2x cubed minus 9x squared plus 12x plus 1. Which of the following is the maximum value on the open interval 0, 4? To find the local maximum of a function, we begin by identifying where the derivative equals 0. These points, called critical points, are potential locations for local extrema. So in step 1, we differentiate the given cubic function using standard power rule differentiation. Once we have the derivative, we set it equal to 0 and solve the resulting quadratic equation. Factoring gives us two critical points within the interval from 0 to 4, at x equals 1 and x equals 2. In step 2, we apply the first derivative test to determine whether each critical point corresponds to a maximum or a minimum. This involves evaluating the sign of the derivative just to the left and just to the right of each critical point. At x equals 1, the derivative changes from positive to negative, which tells us the function reaches a local maximum there. At x equals 2, the derivative changes from negative to positive, indicating a local minimum instead. Now that we've identified the location of the local maximum, we move to step 3 and plug this value of x back into the original function to compute the corresponding function value. This final calculation gives us the maximum value of the function on the open interval from 0 to 4. Putting it all together, we know that the local maximum occurs at x equals 1 and the maximum value is 6, which corresponds to answer choice B. Practice question 3. Find the value of the mixed second partial derivative of the given expression evaluated at the point 0, 1. We start by computing the first-order partial derivative of the function with respect to x. In this step, we treat y as a constant. The function is composed of two terms. One is a polynomial expression, and the other is an exponential expression involving the product of the two variables. The derivative of the first term with respect to x gives a linear result involving both variables, while the derivative of the second term uses the chain rule, since it involves a composition. That gives us an expression that includes the exponential function multiplied by y. Once we have the first partial derivative with respect to x, we then take the result and differentiate it again, but this time with respect to y. For this second derivative, we again apply standard rules. The derivative of a product in one term requires the product rule, and the derivative of the other term is straightforward. When we complete this step, we arrive at an expression that contains three terms, one from the linear part and two from the exponential term and its derivative. In the final step, we substitute the values 0 and 1 for x and y, respectively, into the expression we just found. Plugging in those values simplifies each term individually. The first and third terms become 0 since they involve a multiple of x, and the second term becomes 1 since the exponential of 0 is 1. Adding everything up gives a total result of 1. This result matches answer option A. Practice question 4. Consider the following scalar field. Which of the following statements is always true about the gradient of f at any point in space? Let's start by evaluating each of the given statements. Option A claims that the gradient points in the direction of greatest decrease of the function. However, this directly contradicts the definition. The gradient always points toward the direction in which the function increases the fastest, not decreases. So, option A is clearly false. Next, option B says the gradient is tangent to the level surface of the function. Again, this misrepresents the role of the gradient. In fact, the gradient is never tangent to the level surface, it's always orthogonal to it. This geometric fact is fundamental in multivariable calculus, particularly when dealing with directional derivatives and surface normals. Therefore, option B is also incorrect. Moving on to option C, it states that the gradient is perpendicular to the level surface of f. This is precisely the key property of a gradient vector and is always true, regardless of the function's specific form. Since the gradient gives the normal direction to the level surface, option C correctly describes this behavior. Finally, option D suggests that the gradient has a constant magnitude. This is not generally true unless the scalar field is linear, which is not the case here. The given function has a gradient that depends on the position in space, as x, y, and z change. So do the components of the gradient vector, and therefore its magnitude changes as well. So option D is also false. Therefore, answer choice C is the only correct answer option. Practice question 5. A particle moves along a curve defined by the following parametric equations. Find the length of the curve traced by the particle over the given interval t from 1 to 2. To determine the length of a curve defined by parametric equations, we begin by using the arc length formula for a parametric curve. This formula tells us that the length of a curve traced by a particle from a starting time to an ending time is found by integrating the square root of the sum of the squares of the derivatives of the horizontal and vertical components with respect to time. The derivative of the horizontal component, t squared plus 1, is 2t. The derivative of the vertical component, natural log of t, is 1 over t. Now we apply the arc length formula. Since the question only asks for the expression and not the evaluated number, we do not simplify it any further after squaring the x and y component derivatives. Therefore, the correct answer is the integral from 1 to 2 of the square root of 4t squared plus 1 divided by t squared with respect to t. This expression matches option B. Practice question 6. Let the curve be defined by x equals y squared. Find the curvature k at the point where y equals 2, using the formula for curvature in terms of dx dy. We begin by using the curvature formula that expresses curvature in terms of the derivative of x with respect to y. Specifically, this formula is the absolute value of the second derivative of x with respect to y, divided by the quantity 1 plus the square of the first derivative of x with respect to y, all raised to the power of 3/2. In step 2, we take the necessary derivatives. First, we find that the first derivative of x equals y squared is 2y, and the second derivative equals 2. Next, We evaluate both of those expressions at the point where y equals 2. Now we plug that into the denominator of our curvature formula. The denominator becomes 17 raised to the 3/2. Finally, in step 3, we substitute the second derivative, which was 2, and the computed denominator into the formula. This gives us 2 divided by 17 to the 3/2. That's the exact value of the curvature at the specified point. The correct answer is therefore option A. Practice question 7. Let the vector field be defined as follows. Which of the following statements is true about the curl and divergence of F? To analyze the curl and divergence of the given vector field, we start by recalling the standard definitions from vector calculus. Step 1 reminds us that the divergence of a vector field is calculated by taking the sum of the partial derivatives of each component of the vector with respect to its corresponding variable. The curl, on the other hand, is given by the determinant of a special matrix that involves the del operator and the components of the vector field. In step 2, we compute the divergence of the vector field, which is defined as the vector with components y, z, and x. The divergence is found by taking the partial derivative of the first component, y, with respect to x, which is 0, then the partial of z with respect to y, which is also 0, and finally the partial of x with respect to z, again 0. Adding all these together, the divergence comes out to be 0. Step 3 moves on to computing the curl. We use the determinant involving the partial derivatives and the components of the vector field. The determinant simplifies to a vector with all 3 components equal to -1. Since this result is not the 0 vector, we conclude that the curl is non-zero. Finally, in step 4, we summarize the results. The divergence is 0, and the curl is not 0. This leads us to the correct conclusion. The divergence of the vector field is 0, but the curl is not, which matches choice C. Practice question 8. Evaluate the limit e to the x minus 1 minus x over x squared. We know that e to the 0 power is 1, so the numerator becomes 1 minus 0, which simplifies to 0. The denominator, x squared, also approaches 0. So this is a classic indeterminate form of 0 over 0. That means we can apply L'Hospital's rule. L'Hospital's rule says we can take the derivative of the numerator and the denominator separately, then try the limit again. The derivative of the numerator becomes e to the x minus 1. The derivative of the denominator is 2 times x. Now we reevaluate the limit of the new expression, e to the x minus 1 over 2x. Again, as x approaches 0, both the numerator and the denominator go to 0, so we still have 0 over 0. This means we apply L'Hospital's rule a second time. Taking the derivative of the numerator, e to the x minus 1, we get just e to the x. The derivative of the denominator, 2x, becomes 2. So we now have the limit as x approaches 0 of e to the x divided by 2. As x approaches 0, e to the x becomes 1. So the whole expression becomes 1 over 2. The value of the original limit is 1/2. So the correct choice is option C. Practice question 9. Find the derivative of the following function. To find the derivative of the function natural log of cosine of 2x, we begin by recognizing that this is a composite function. The outer function is the natural logarithm, and the inner function is cosine of 2x. Because this is a composition of 2 functions, we'll use the chain rule. In general, the derivative of the natural log of u, where u is a function of x, is equal to 1 over u times the derivative of u with respect to x. So, we set u equal to cosine of 2x, and now we differentiate. The derivative of cosine of 2x with respect to x is negative sine of 2x times 2 by the chain rule. That simplifies to negative 2 times sine of 2x. Now using the chain rule, the derivative of the original function becomes 1 over cosine of 2x multiplied by the derivative of the inside, which we just found to be negative 2 sine of 2x, Multiplying these gives negative 2 sine of 2x divided by cosine of 2x. So the final derivative corresponds to answer choice A. Practice question 10. A farmer wants to build a rectangular fence along a straight river. No fencing is needed along the riverside. She has 240 meters of fencing available and wants to enclose the maximum possible area. Which of the following expressions correctly represents the area A in terms of a single variable x, where x is the length of the side perpendicular to the river? We're told a farmer is building a rectangular fence along a straight river. Importantly, no fencing is needed along the riverside. That means fencing is only needed on the two sides that are perpendicular to the river and one side opposite the river, forming 3 fence sides total. We start by defining variables to describe the situation. Let x be the length of the side perpendicular to the river. Since both of those sides are the same, and there's one more side parallel to the river with length y, the total amount of fencing used is 2 times x plus y. We're told there are 240 meters of fencing available, so the equation becomes 2x plus y equals 240. Next, we solve for y in terms of x. Rearranging the equation, we get y equals 240 minus 2x. This gives us a single variable expression for y, which we'll use to write the area. In step 3, we recall that the area of a rectangle is base times height. In this case, x times y. Substituting in the expression we just found, the area becomes x times the quantity 240 minus 2x. This gives a final area function of A of x equals x times 240 minus 2x. This expression represents the area in terms of a single variable and corresponds to answer option C. That concludes our practice questions for this unit of mathematics. In the next lecture, we will continue with mathematics and cover topics within the scope of differential equations and transforms. Again, if you want more example questions for mathematics or complete FE practice tests, visit the link in the description or on screen. Thanks for watching.